So we were talking about hypothesis tests, and we had done hypothesis tests for proportions, and we want to do, the next step is to do hypothesis tests for means, mu. But I do want to just, because it's been a little while, I want to remind you how hypothesis tests for proportions work. So somebody has made a claim about some proportion p. We turn that into a null hypothesis and then an alternative hypothesis. So the null hypothesis is that p is something, so there would be some number here. And the alternative then is that it is less than that, or it could be that it's greater than, or it could be that it's just simply not that number. There are three possibilities for the alternative hypothesis. Remember that the null hypothesis is always equals, and the alternative hypothesis is always one of these three things. So one of these is what somebody is claiming, and then the other one is sort of the opposing claim. We also then have the significance level alpha. Often this will be 0.05, but it could also be 0.01, and recently there's been more of a push to have it be smaller, like 0.01. But 0.05 is the old traditional value. All right, what happens next is that we then go out and collect a sample, and the sample, we take a sample of size whatever, and we see how many are whatever it is we're counting, number of left-handed people or whatever. Okay. Then there's the test statistic. You take your p up here, and you turn your sample. You figure out what your sample p is. So p hat. And so you have your p and from the null hypothesis and your p hat, and you put that all together here, and you get a z. And this z has a standard normal distribution. Sorry about the messy picture here, but standard normal, which is what z always is, and then you use your calculator or a z table, a z chart, to turn that into a probability, and that's called the p-value. Okay, and then the thing is, you compare the p-value to your alpha. So your alpha was like the critical p-value below which we're going to do something special. And here's how that works. If your p-value is less than alpha, then we say that our sample, our data, was statistically significant, and we reject the null hypothesis. Otherwise, we don't. If the p-value is bigger than the alpha, we don't reject the null hypothesis. Okay, so it's like the null hypothesis is on trial. We look at our data and see if our data is sort of plausible in a world where the null hypothesis is true. The p-value is the probability of getting what we got in a world where the null hypothesis is true, and we see if that's super small, because if that's super small, then maybe we don't live in a world where the null hypothesis is true, because it's too unlikely to have gotten what we got. So that's the idea. All right. Of course, we can streamline this on our calculators. Our calculators will do the all the calculational work for us, and that's called the 1-prob-z test. And then one more thing, which I don't think we talked about in class, is what you need to have be true in order to do the 1-prob-z test, or what's on the previous page. And it's kind of the same as for a confidence interval for p. Your data has to come from a good, simple random sample, as always. You need to be in a sort of a binomial situation, which means you're doing a bunch of trials. They're all independent, and they come out in one of two ways. So left-handed or right-handed, something like that, right? And then thirdly, you need n times p and n times q to be more than 5. And that part justifies using the z table, because really it's binomial, but that's kind of clunky and hard to work with in this context. So we want to just use the normal distribution, and these two justify that. If these two are big enough, then binomial is close enough to a normal distribution that it's fine. Okay, so that's the idea. Let's do an example before we move on to the test for mu. So suppose that somebody claims that a drug screening test is incorrect 10% of the time, but the company says, no, we do better than that. The percentage that's incorrect is lower than that. All right, so we can turn this into a hypothesis test. On one hand, we say the null hypothesis will be that it's 10%, and the competing claim is that it is, less than 10%. Here, P is the percentage that is of times it's incorrect. All right. And let's just go with a traditional 0.05 significance level. All right. So that's the setup. All right. Now we have our data. And so we go out and we sample. We do 300 subjects and we put them through a drug screening test. And suppose this is a test of the test, so we know whether the 300 subjects have drugs in their system or not. So we can tell if the screening is correct or not. And suppose it's incorrect 27 times out of 300. So our p hat is 27 out of 300, which is 0.09. So it is less than 10%, it's 9%, and the question is that enough below 10% for us to say the real number is not 10%, it's actually smaller, maybe 9% or whatever. Okay. So in this case, I'm just going to let my calculator do the work. We've done this more manually in the past, in a previous class. And when I put it into my calculator, I get a p-value of 0.282. Okay, so 28%, 0.282. So that means that if p really is 10%, there's a 28% chance of getting these results, or even smaller. So that's not too small, and it's certainly not less than 5%. So this could have happened in a world where the null hypothesis is true, right? So our conclusion is it's not statistically significant. We do not reject the null hypothesis. P could certainly be 10%, and we haven't found evidence to the contrary. Okay. So that's just a review of what we've already done, and in the next video we'll now switch to doing hypothesis tests for what a mean mu is.